Hi, I'm Mr. V, and this is Illustrative Mathematics. We're in geometry, solid geometry, chapter 5, and this is unit 6, which is about scaling solids. And the objective, by the end of the period, you should be able to say that I know that when a solid is dilated by a scale factor of k, its surface area is multiplied by k squared, and its volume is multiplied by k cubed. And if I were to look at some of the stuff that we've done before, we knew that if we scaled an object by or a length by k is proportional to the k. So we multiply the length times k to get to the new length. And in area, if we have a length and a width, and we're scaling both of those, you're scaling the one by k and the other one by k, so you scale it by k squared. Well, today we're going to look at solids, and we're looking at two parts of them. One is if it's the volume, it's going to have a length, a width, and a height component. So it's going to be times k cubed. Or if we're looking at the surface area, the area of just the surface part of it, that's going to be similar to what we did when we looked at a two-dimensional object of area. It's going to be multiplied by k squared. That's going to be the objective of what we're looking at accomplishing today. So on each of the next 4 pages, you were supposed to do these without a calculator. If you haven't done them, please pause the video and try this. And I gave students about 5 minutes to do that. Finding the answer is just one part of it. Really what I'm looking for is how do you explain your answer? So it's like an open response. I want you to tell me what was going on in your head to do this mentally. How did you come up with this mentally? And it's not enough to say, well, I just did it in my head. I want to know what was going on in your head when you did this. Some answers that I have seen earlier. So if I have a 2 by 2 by 2, to find the volume, I know that the volume is the length times the width times the height in a rectangular prism. You could say it's the s cubed, which is a misnomer. It's not the sides cubed because three-dimensional objects don't have sides. They have edges, faces, and vertices. So we could have said edge cubed better, but this is the formula that sometimes is given. And in your head, maybe you went 2 times 2 times 2. And 2 times 2 times 2 is equal to 8. So you said the answer is 8. Don't forget about the units. The units here is meters cubed. That is because I have meters times meters times meters. Length times width times height. Meters times meters times meters is meters cubed. And the answer is 8. For the next one, doing it in my head, this might be a little bit harder. You got 5 times 5 times 5. Oh my gosh. But if we do 5 times 5 first, that's a quarter. And how much is 5 quarters? Well, I know, everybody knows that's $1.25. So $1.25 feet cubed. That's what we're looking at. And this is how I did it in my head. I said, well, 25. 25, 5 quarters. Okay, $1.25. 1 times 1 times 1, that's the answer is going to be 1. Because 1 times 1, it's not 3. We're not adding these. We're multiplying. I had one student try to add them together. No, it's going to be multiplying. And the last question is a little bit trickier. And I noticed right away if a student was using a calculator when they weren't supposed to, because those students that use a calculator invariably tell me that this is equal to 0.125. And it's like very difficult to get to this from this if you're doing it in your head. One girl said, if I'm going to multiply these, I would multiply 1 times 1 times 1, and I would multiply 2 times 2 times 2 to get 1 over 8. And this is correct, 1 over 8, and this is inches cubed. So when we look at this in the Desmos, there's some discussion about this. One of the questions was, some of you may be unsure how to do this. One way to do it is to look at this ruler. If I take half of 1, that's 1 1/2. And if I take half of that, that's half times a half, it's 1/4. I take half of that, that's half times a half times a half, which is 1/8. And if you work with wrenches, maybe your wrench sets are going to be 3/16 and 7/16, and this business of the royal units of feet and inches and stuff. This would be something very typical for you to see. It might be easier to see with wrenches as well. Maybe you looked at the box and you divided up the box. If you divide it into half, slanted wise, like this, and then cut that in half, and then cut that in half again, you end up with 1/8. And it might be easier to see if you use this this GeoGebra applet on the next page. So on the next page, I have a GeoGebra applet, this one. And notice I have a 1 by 1 by 1 cube. And my surface area, my volume, is 1 times 1 times 1. So it's 1. And the surface area, well, the surface area of one of the faces is 1 times 1, which is 1. And how many faces are there? Well, there are 6 faces in a cube. So my surface area is 6 times 1. And this is which is 6 units. If I do a 2 by 2 by 2, which we can make this a 2 by 2 by 2, first of all, I would like to say, I asked students when we built these by hand, we built some of these with business cards. And I would say to them, if I double the edge lengths to make a larger cube, how many times larger is the volume of the new cube? And they'll tell me it's double. And I'll say, you mean like this? No, it's 4 times as much. You mean like this? And it's kind of funny because they always say the same thing, and I can expect it. If they don't say that, I'm kind of, why didn't they say that? No, it's going to be 8 times as large. And if I have another GeoGebra app, maybe it's easier to see it in here. If I can make this thing a filling, you can see filling. You can see this. If I turn this around, you can see it's going to be 8 cubes. And the surface area of this one, so my volume is 2 times 2 times 2, which would be 8. And my surface area, we can create a net, we can unfold this thing, is going to be 4. And there's 6 of these, 1, 2, 3, 4, 5, 6. So it's going to be 6 times 4, which is 24, is my surface area of this thing. So 6. And the area of one of them faces is 4. So it's going to be 6 times 4, which is 24. What do you think it's going to be for a 3 by 3 by 3? Well, let's just try it. 3 by 3 by 3, maybe make this smaller so you can see it, is going to be, well, there's 9 blocks on the first layer, 9 more on the second, and 9 on the third. That's 3 times 3 times 3, which is 27. 4 times 4 times 4, 64. 5 times 5 times 5, that's 5 quarters, 125. And 6 times 6 times 6. Let me see if I can make this where I can see it anymore. Make it a little bit better. 6 times 6 times 6 is 216. What about the surface area? A 3 by 3, I'll do it with this one, 3 by 3, length, width, and height. And if I unfold this, so if I make this more solid, and I unfold this with a net, I've got, each one of these is 9. And there's 6 of them. How did I get 9? I did 3 times 3. I get 3 times 3 is 9, and I times 6, which is 54. 10 times 6 is 60. 9 times 4 is 6 is 54. What about 4 of these? 6 times 16, that's 96. We have 6 times 5, which is 6 quarters, of course, is 150. And 6 times 6 times 6, we've already done this, 216. What's interesting to notice about this, and what I want you all to pick up on, is that if I have my scale factor, my volume is going to be the scale factor cubed, because my original volume was 1. Here we have a surface area is going to be 6 times the scale factor squared. What? Where does that 6 come in? Why is it 6? I thought you said it was going to be the area times k squared. Well, it is. It's just that my starting area isn't 1. My starting area is 6. I had 6 faces to that 1 by 1 square. So 6 is my starting. If I had started with something other than 1 here, it'd be some factor times k cubed. This doesn't have a factor because my starting volume is 1. Isn't that interesting? Now, in the Desmos activity, there's several other points to go along with after doing this table. But this table is the big part of what we're doing. The questions are on page 11 and 12, which we just went through, and the synthesis on page 13. Now, on page 14, Elena and Claire are having this discussion about, well, how do you prove that it's always going to be k cubed? And in the same way, maybe you remember us when we did a blob. We did this with an area. We said, Well, we know that an area of a rectangle is the length times the width times k squared. And we could fill this thing full of rectangles like this, little rectangles and little rectangles. And you scale each one of them by k squared to make it larger or smaller. So sure, the blob is going to be scaled. The area that you end up with, is going to be the area that you start with times k squared. And we did that with blobs. If you do that with cubes, you do the same thing. And there's actually this fellow, his name is, what is his name? Nathan, I forget his last name, Sawaya. Nathan Sawaya. I think he was a lawyer in New York, and he quit his job to glue Legos together. And he's really famous, actually. And he's done many, many things. He's made these exhibitions that go all over the world and in museums, and he sells these things for like a bundle of money. This one's the scaling down of the parliaments we're building. Here we have you have the Venus de Mayo and the David and Caesar, and he's done these, and he scaled these up or scaled them down using cubes. And that's what we're talking about doing, is using a bunch of little cubes and scaling things up and scaling things down. And sure, it's going to be k cubed. And that's the big idea between what I'm saying here, is that it's going to be a factor of k cubed. So let me see if I can find my thing here. So in our excuse me, in our Desmos, on page 17, page 13, there's a question. I think it's 13, page 14, the question. Suppose you have this prism, and I'm going to go to my whiteboard so you can see it. Suppose you have this triangular prism. It has an area of 84 square centimeters, a volume of 36, and it's got a scale factor of 4. We want to know what the calculated area would be after you dilate it by a scale factor of 4. Where do you begin? You begin this by writing the formula, substituting the values, and then solving. And so our surface area to begin with is 84. Our volume to begin with is 36. And our scale factor is 4. So the formula for the area, it's going to be your starting area times k squared will get you the new area. And so if we multiplied 4, not 4, but 4 squared times 84, this would give us our new volume, and it's going to be in centimeters squared. Notice how this is squared, and this is squared up here. And this has 2 dimensions. It's got a length and a width component for surface area. In the volume, the formula is the volume that we start with times k cubed is equal to the second volume. So here we have to do the 4, but not times 4, it's times 4 cubed. 4 times 4 times 4 times 36. And again, this will give you an answer, and the units are going to be centimeters cubed. There is a summary page here, and if you would please read it, the lesson summary. This is the big synthesis of this whole thing is right here. This should find place in your notes. When a solid is dilated by a scale factor of k, its length is scaled by k. Its area is scaled by k squared. Why? Because a times c for this front face. Here we have ka times kc, which is a times c times k squared. The volume is by k cubed. You have a times b times c. Here we have a times b times c times k times k times k, or k cubed. And this is the big idea. I summarized it in my page over here with this. And that's one way of looking at it. And for the cool down, consider a cube. It's 1 inch on the side, and each one of these sides is 1 inch. And we want to know what is the volume in cubic inches when you scale this 1 by 1 by 1 to make it a 12 by 12 by 12. And our scale factor is going to be 12. And our initial volume is going to be 1. So what we want to know is, what is our volume going to be when we get there? It's going to be k cubed times the volume 1. So 1 times 12 cubed is going to give me my answer. And it's going to be in inches cubed. And I'll let you put that in the calculator. So hope this makes sense to you. Good luck and success.